Hey guys, welcome back to day 10. We're going to talk about Arrhenius and catalysts today. We're going to dive into how do reactions happen. Right? Have we ever thought about how they actually happen? We understand that there's reactants and reactants go to products, but do we ever think about how do the chemical reactions happen? Right? There's only two really ways to do this. All right? There's two different ways to do this, and that would be breaking a bond and then making a new bond, or making a new bond and breaking the old bond. Very similar to dating. I'm glad I'm done with dating. So a reaction is a rearrangement of atoms. So a reaction is a rearrangement of atoms. Bonds must be broken and new bonds formed. It's also a redistribution of electrons. So electrons are moving, atoms are moving, bonds are broken, bonds are formed. 3 points. 3 points. The first one is atoms. Atoms and molecules must collide or be pretty darn close. There's a harpoon mechanism actually you can learn about, but that is not the norm, and they still have to be close. So atoms and molecules must collide with one another in order to react. That kind of makes sense. In order for me to yell at my kids for one of them hitting the other one, they actually have to make contact. They might have tried to hit, but if they didn't hit, they didn't hit. So got to actually have contact, collision. In that collision, there must be sufficient energy. Sufficient energy must be available to break bonds that need to be broken. The last point, the orientation of the collision must be appropriate. The orientation does matter. So when we're talking about especially bigger molecules, the orientation really matters. Where these molecules interact. You might have heard of like enzymes and active sites and stuff like that, because these molecules are enormous compared to small molecules like propane and oxygen gas. No matter what happens with propane or natural gas methane, when they hit, the reaction is in a favorable condition. But when you're talking about a huge enzyme and a huge molecule going into the enzyme, all of a sudden now orientation factor is really important. Okay, so we'll start with this, the obvious that the collision has to occur, and we'll get to the orientation. Let's talk about the energy. Temperature and reaction rate. Because we know that the temperature usually increases, that means the rate usually increases. It's not 100%. I'm sure we're going to find an example. You could probably Google it find an example where if it gets colder, it goes faster. But majority of reactions, as we increase temperature, they go faster. So the rate of a reaction will be equal to the rate constant K, and that's where the temperature dependence is located, to the concentration of any reactant A to that power. We don't know the power, the order. I'll use a light blue. There we go. That's fun. Okay, so the temperature dependence of the reaction rate is contained in the rate constant K. All right, and again, in general, as temperature increases, the rate increases. All right, faster reaction. Okay, so now the famous chemist, savante, which I like his name, Arrhenius, right? He was the one that gets credit for temperature dependence to the rate constant. All right, so the rate constant K is equal to this thing we're going to call A E to the negative EA divided by RT. So what are the factors? Obviously, K is the rate constant. And T, of course, is temperature. R is R. Right, R is R. And R, in this case, would be 8.3145 joules per Kelvin mole. Because we don't have liters, we don't have atmospheres. A. This A, what is A? A is broken down into two. It's the pre-exponential term. So it's not the same as this A on the top of the screen here from the rate constant. It's not the reactant concentration, right? That one's blue, this one's purple. It's purple for a reason. It's different than this blue one, okay? This A is just the pre-exponential term. It broken down into P and Z. P and Z. All right, P and Z. So P would be the orientation factor. Right, and it goes from 0 to 1. So 0 would be very strict. 1 would be any. Okay. So very strict to any. If I have a well, just for human behavior, going in the front door, there's pretty much one door to go into if you're going in the front door. Right? No matter what the house is. Now, there are some places, like car, if you want to get to the driver's seat, if it's a two-door car, you can get to the driver's seat from any side. But there are some places, right, where the orientation factor really matters. For even human behavior. For chemical behavior, it's the same thing. So a lot of times larger molecules have a very strict orientation that needs to happen for them to work. The smaller molecules typically have any, and I think we'll go into that more. Z is the collision frequency, and it's typically around 10 to the ninth, which is quite large. And usually, I think for most of our purposes, P is going to be more important than Z. But again, that's not always true, right? But most of the time, the orientation factor is going to be the more limited factor in that. Last but not least is EA. And EA is probably the most important thing, activation energy. And activation energy is the energy required to make the reaction happen. All right, again, human behavior, nothing to do with chemical behavior. Like decision-making human behavior, nothing to do with chemical behavior. So my kids, they have a toy room, and in order to facilitate the energy required to clean the toy room, a lot of times something has to be taken away, and all of a sudden, magically, the energy is available to clean the toy room and get the Legos off the floor. It's just shocking how that works. If there's no consequence, there's Legos on the floor. All of a sudden, if we can't do something we want to do, Legos are picked up. It's amazing. All right, that's activation energy. For some of us, that's getting out of bed in the morning earlier than we necessarily naturally would do. There's all sorts of different things when it comes to the human decision making, what drives us. In chemical reactions, this activation energy is the minimum energy for the reaction to occur. This just has to happen. It's not going to happen otherwise. All right, it's a minimum. It's a barrier, so to speak. And once you beat the barrier, you can go. It's almost like if you're trying to throw a baseball or a tennis ball or some type of ball over the roof of a house, whether it's a one-story roof or two-story roof. That's just how big the activation energy is. So if I have a one-story house and I'm trying to throw a baseball over the roof or a tennis ball, just throw it and it hits the roof and it comes back to me. Right? It's not enough energy. So no matter what, a lot of times little people, especially, they throw that ball over the roof. It's not going to happen. So it keeps coming back. Eventually, you get one that goes over, right? And go to a two-story house. Now that activation energy is higher because it's harder to get that particle over, right? That's very similar to what's going to happen with these activation barriers. And so a figure for this, right? Activation energy is right here. This blue is EA. And blue in that one. Now, delta H, right, because energy, joules, reaction progress, right, if that's pretend that's a magically straight line right there. That is delta H, which is different than EA. So EA is kind of, think of it as a roller coaster. I have H2 and O2, which these guys really want to react. And so activation energy is a spark. It's not that large. It's more than room temperature, though, right? Because if you have a balloon of hydrogen and oxygen, it's not going to react until you have the spark, and then boom, violent, fast reaction. So it's kind of like the roller coaster going up, and once you get to the top, you can go forward. And once activation energy is met in a lot of these reactions, the temperature's there, and they just keep going. So delta H is the overall change. EA is more about how we get there. All right, and this next picture to the right shows that the area underneath the blue curve is the area underneath the red curve. What's the difference? Well, the red curve is warmer. And so the more of the area underneath the red curve is past EA here. I'll use blue because that's what they used. And so since more is past, like I guess it's more of an orange shaded, is larger than the blue shaded. All right, so this curve, since we warmed it, we kind of flattened it, so to speak, and spread it out so that more is past the activation barrier. All right. Now, when you look at this, the difference between T2 and T1, so if I increase temperature, two things happen. One, we increase the number of collisions. which is good. 2, we increase the energy in the collisions, which of course, number 2 is much more important. Because the collisions are good, but you having enough collisions to transfer energy, have the energy react, that's better. Right? That is better. Okay, so now if we go back to this form, all right, we go back to K. That's all, it always looks like a capital K. K, it's a lowercase k, equals A E to the negative EA RT. Just like that. Well, we can do some math and take the natural log of K. So rearrange and get rid of the E. Natural log of K equals negative EA over R times 1 over T plus the natural log of A. And you might recognize that looks like y equals negative mx plus b. And that's what you would look like. And so that's the Arrhenius equation. So we like this one right here. But then we're going to use also a 2-point form. If you remember, like the Clausius-Clapeyron equation and whatnot, where the natural log of A is the same. It's in this case it's the y-intercept, so you can have any two temperatures and any two k's. And so depending on how it's derived, the natural log of the two k's equals EA over R 1 over T minus 1 over T. And whether it's T1 and T2 or T2 over T1 plus minus, that all matters. So we got K's, the two K's. I do K. K. Well, let's make the K's. We'll do EA in red. So T1 on the bottom, T1 here. The way I have it in this, and then we have T2 up here, and sorry, K2. I'm backwards. T2. Let's go with K2 here. And finally, K1 there. That's much better. There's our 2-point form, finally. So those are the two Arrhenius equations we will use to solve problems. And I think right here is the first one. The rate constant of a reaction at 32 degrees Celsius is 0.055 per second. So that's K. Rate constant, that's K. The frequency factor, A, right? What's the activation energy? That's the question, EA. So this is a 1-point form. So K, the rate constant, equals A, E to the negative EA divided by RT. Okay. Well, what would I do to solve this? Well, let's just plug numbers in and go for fun. 0.055 seconds to negative 1 equals 1.2 times 10 to the 13 seconds negative 1. E to the negative EA, which we're looking for, R, 8.3145 joules per Kelvin mole, and T. And T in this case is 32 degrees Celsius, which plus 273 was that 305. We're looking for EA. So what do we do? Well, the first thing we would move, I would move the purple number over and then take the natural log of both sides. So I end up with the natural log of the, well, let me just keep writing, 3145 joules per Kelvin mole here. We have in orange 0.055 seconds negative 1. In purple, 1.21 times 10 to the 13 seconds negative 1. Those units will look like they cancel. I have a temperature over here of 30, didn't change colors, did it? 305 K. And then I have EA. So we can do the natural log and then times everything by the negative 8.3145 and 305. So what will that look like? It looks like the natural log of 0.55 divided by 1.2 times 10 to the 13th times negative 8.3145 times 305. And I get 83727. And sig figs, it looks like I have 2, so 84,000 joules. Or 84 kilojoules. And that's what I get for number 62. Number 70. Now number 70 is same thing, except we have 2 rate constants and 2 temperatures. A, we're looking for EA, activation barrier, EA. And so we'll do green and blue. Now, of course, we have to convert these to temperatures. We have to add to Kelvin. So 27 Kelvin would be 300 K, right? And 77 is 350 K, right? Because we're adding 273. Okay, so for A, I have the natural log K2 over K1 equals EA over R 1 over T1 minus 1 over T2. So plug in these numbers. Natural log. All right. K1, I'm going to put on the bottom in green. 0.00122 seconds negative 1. K2, I'm going to use 0.228 seconds negative 1. I just want to point something out real quick. Look, that's 50 degrees Celsius, which is quite a big increase in temperature. Look how fast, much faster. It's 3 orders of magnitude faster. Right? 3 orders of magnitude faster. That's a big difference. Equals, we're looking for EA. R is 8.3145 joules per Kelvin mole. 1 over minus 1 over. We're looking for EA. All right, T1 in green, 27 degrees Celsius or 300 Kelvin. And T2 in the light blue is 350 Kelvin. Okay, so how do I solve this? Well, calculator. Do the natural log first. So natural log of 0.228 divide 0.1230 122. I missed the 1. 22. All right. Then we are going to times it by 8.3145. Then we're going to divide it by the fractions, the temperature, 1 over the temperatures. All right. 1 divided by 300 minus 1 divided by 350. It's not working. Minus 1 divide 350. There we go. Yes, I find touchscreen calculators very problematic. I don't know if you guys do as well. There you go, 131,531. 131,531. Or really 2 sig figs, 130 kilojoules per mole. There you go. 2 to 3 sig figs would be 132 kilojoules per mole. For 2 sig figs, 130. B, all we're doing now is looking for a K, right? And so instead of, now I'm going to use the light blue ones because they're smaller numbers, right? You can use the green ones. It doesn't really matter. Let's use the green ones. So here, natural log K2 is what now I'm looking for. K1, I'm going to keep it as 0.00122 seconds negative 1 equals, we got 131,531 joules per mole. You can use that. You can use the 130,000. It's really not going to make that big of a difference. R, 8.3145 joules per Kelvin mole. And we got 1 over minus 1 over. Now, green, 300 Kelvin. And let's see, we had 17 degrees Celsius here in orange. Well, what's 17 degrees Celsius? So, right, that would be 290 Kelvin. Okay, how do I put this in my calculator? 0.000122 times the second natural log, right? E to the, open my parentheses, 131,531 divided by 8.3145 times 1 divided by 300 minus 1 divided by 290. And I need a second parentheses there. And let's see, I get 1.98 times 10 to the negative fifth, or basically 2.0 times 10 to the negative fifth. And that works out wonderful. And the second's negative 1 because that unit is still there. So that is Arrhenius. I hope that clears some things up. Stay tuned for the next one.